Variations in value of small g. Change along the surface of the earth. Will the value of gravitational acceleration be same everywhere on the surface of earth? Answer is no. The reason is that the shape of the earth is not a perfectly sphere. Due to its rotation, the earth bulges at the equator and is flatter at the poles. Initially, the earth was in the gaseous state, then it turned into liquid state and then into solid state. And due to its own rotation, the shape is like this. That means if you take the radius near the poles, that radius is slightly lesser than radius at the equator. Now this has an effect on the value of gravitational acceleration. We know that small g is capital G, capital M upon r square. So if we consider the gravitational acceleration at the poles, Gp equal to Gm upon Rp square, which is a smaller number, and gravitational acceleration at the equator is capital G, capital M upon Re square. Now we know that radius at the equator is slightly greater than radius at the pole. So here the value of the fraction is little bit greater, and when the value of fraction is more, when the value of the denominator is more, Re square is the denominator. When the value of denominator is more, value of fraction is less, and when value of the denominator is less, value of fraction is more. That means if we consider two fractions 1 by 2 and 1 by 3, we know that 1 by 2 is greater than 1 by 3. It's like this. This is 1 by 2 fraction and this is 1 by 3 fraction. So this is smaller than this. So gravitational acceleration at the poles and gravitational acceleration at the equator. At the equator the value is smaller because denominator is greater, and value at the pole is more. This is because the radius is smaller there. Same thing is given here. Due to its rotation, earth has bulged at the equator and little bit flattened at the poles. Its radius is largest at the equator and smallest at the poles. Value of g is thus highest, 9.832 meter per second square at the poles, and decreases slowly with decreasing latitude. It is lowest, 9.78 meter per second square at the equator. So this is the first change in value of g along the surface of earth. Now if we go to greater and greater height, value of g will decrease. It is same logic, means when we talk about the gravitational acceleration at a height, the formula is small g is capital G, capital M upon r plus h the bracket square, and when h becomes a large number, value of r is 6400 kilometer, radius of earth. So when the value of g h is comparable to the value of r, then there is a drop in this value of g, and that drop is considerable if value of h is considerable. If value of h is small, like 10 kilometers or 8.8 kilometers as on the Mount Everest, the change in value of gravitational acceleration is not very prominent. It is not considerable. It is negligible for small heights. On the other hand, when we consider an artificial satellite which is at 35,700 kilometers from the surface of earth, there is a large change in value of h, and which brings about a considerable change in value of g. Some typical heights and the value of gravitational acceleration are given here. At the surface of Earth, value is 9.8. At Mount Everest, it is approximately same 9.8. Highest height reached by the man-made balloon, 36.6 kilometer, value little bit drops to 9.77. Typical weather satellite, 400 kilometer, value is 8.7. So there is a drop of almost 1 meter per second square. But at a height of communication satellite, value has dropped to a very large extent. It is 0.225 meter per second square. So this is how the value of G changes with the height. Third thing is the change with the depth. Means if you dig the earth and go deeper inside, what will happen to the value of G? At first, we may think that value of G will increase with the depth, and this is because as we go deeper at a depth, let us say D, the radius will decrease and the value of G will be capital G capital M upon R minus D square. But we must not forget that for that value of M will also change. The value of M which is contributing in this gravitational force, only this part of the earth will contribute in that value of gravitational force. This part, the outer part, will not contribute. So not only that this will change, but also this M will also change. And what will be the change in value of M? Mass is equal to density multiplied by volume. So rho is suppose density of earth, and volume of that remaining part, this middle part, is pi r minus d cube. And now if we put the value of this M dash in the formula of G, you will get something very interesting. It is capital G rho 4 by 3 pi r minus d cube divided by r minus d square. So r minus d square cancels out. You get the value of G to be equal to 4 by 3 capital G rho pi into r minus d. And then that inverse proportion is not at all there. It's actually direct proportion. So if this value is decreasing, r minus d, as the d increases, r minus d will decrease, and that will decrease the value of gravitational acceleration. So the value of G also changes if we go inside the earth. Value of small r, that is r minus d, in equation 5 decreases, and one would think that value of G should increase as we go down, as we go deeper inside the earth. However, this is important, that the part of the earth which is contributing towards gravitational acceleration force also decreases. That means mass also decreases, and the change in mass is directly proportional to r minus d cube, which means that value of M to be used in equation 5 also decreases. As a combined result of change in value of small r and M, value of G decreases as we go deep inside the earth, and hence we see that value of small g decreases as we go deep inside earth.